everyone. Welcome to the weekly CTP Pass seminar. Today we have a pleasure to listen to Adam Bednorz from the Department of Physics of the Warsaw University. We heard already Adam last year, his approach to relativistic quantum measurement theory. Today we will hear something very different, as far as I understand.
Yes, very different.
Very different. So Adam has been working on tracing the errors of modern so-called quantum computers, quantum machines, or quantum simulators, however you call them. And today we'll have a talk on that. Adam, the floor is yours.
Okay, hello everybody. So it's a pleasure to be here again. As Jarek said, I will talk about something different than relativity. It may be connected to relativity. Certainly, quantum mechanics is not always relativistic, but we will see a different phase, so to say, of quantum mechanics. Quantum resources, something which we need, which people start to sell by selling an access to quantum computers, some public, some private, some Google, and so on. And the question is how good they are. And I will show you an idea how to verify. You can imagine yourself, you go to a shop, and say, give me good apples, yes? And now you want to have a way to verify, is he cheating me or not? Yes? So now you go to IBM, to Google, to Amazon, whatever. Okay, and want to buy some access to quantum computers. And now you ask, do they cheat me? Yes, and now it's much more expensive than just a few apples. Okay, so the main actor here, or the main hero of this story, is a qubit. Qubit is the simplest but the most useful thing in quantum computing, not only quantum computing, in quantum cryptography and so on. Everything is built like bricks for computers. Qubits are for quantum computers. The difference is that now we are working in Hilbert space. So the qubit is described by two states. The basis is a vector described by two complex parameters that could be reduced by a global phase. So in practice, we talk about some density operators. And now this qubit is a basic unit of memory of quantum qubit, something which we make operations on. The Hamiltonian is usually very simple. It's not the only, because we talk about photons in a minute, but qubit is organized in such a way that the frequency or energy of state 1 is different from the energy of the state 0. And this different frequency is a working frequency, drive frequency, you can call it in a different way. And it helps to make some operations on qubits. Okay, so on the market, there are at least three technologies how to construct qubits. One is quite old one, photons. You have two polarizations of a photon, horizontal or vertical, or some combination of them. The drive frequency is 0 just because they are just different by polarization. So you don't differ them by frequency. Of course, you can have photons of different frequencies, right? But usually we talk about just polarization state. Photons are very good because they can move. So they are very good in, for example, bell test, when you want to send at large distances. The disadvantage is that they are lossy. You can easily lose the photon. It can be absorbed. Just before this talk, I learned that they are improving the coherence of photons. So photons have now close to a second coherence time by some special cavities. Okay, so that's why one of the possibilities. Another is transmon. Transfer is based on superconducting effect, Josephson junction. You combine it with capacitance, and you produce a kind of artificial quantum well. So you remember square wells from studies. Here, this is not a square well, but also it is not a harmonic square, which is very important because harmonic wells are hard because the frequency between higher cells, so there are more states, 2, 3, and so on, and the frequencies also scale linearly, so it is difficult to distinguish between higher states. I will talk about it later. Usually in practice, this drive frequency is about 5 gigahertz. They are quite stable. So, for example, IBM is using it's one of devices for over a year. It has to be calibrated from time to time, of course, but it's not that you cannot lose. They need to be connected to perform the 2-qubit or multi-qubit operations. Isolated. The coherence time is maybe not very long, but you can do something useful. This coherence usually says about how long does it take to keep the state in a certain superposition between 0 and 1, and how long does it take to relax, because the ground state is 0, and after a long time the state collapses to 0. This is a basic picture. It can be more advanced, but this is the main effect responsible for the coherence. And the final technology is, I don't know which one is better, but the last option is trapped ions. Trapped ions are a bit different. They work on the structure of levels of ions. They are using usually Ethereum ions. There is some subtle hydrogen splitting, which is about 12 gigahertz. To drive between levels, it's more complicated, but the good thing is they are very long coherence, just like atomic clocks. So the idea is very close to atomic clocks. They are connected not directly, but by lasers. So if you shine a laser on two of these qubits of ions, then there is some kind of connection. What is important, you need to decouple them from other states, because then it's not a qubit, it's a qubit, and so on. You also need to also to decouple from other states. You need to detune, so they have to have a unique frequency. Imagine a radio. Yes, in Polish you have in Poland you have Radio Z, Radio RMF, and some others, and each one has a different frequency. So qubits are like radios, so they don't interfere.
Excuse me.
Yes.
May I ask a very stupid question?
Yes.
Because otherwise I will be lost for the rest
Okay.
of your talk. You have Hamiltonian, which looks very simple and general, and then it describes things so advanced like trapped ions with finite coherence, etc. Do you cheat, or where is this information stored? Because the Hamiltonian looks simple.
Yes, a very good question. Our world is consists of milliards of qubits, and they are all over the world. So it took years to isolate these two level states, and so it's not that this is the Hamiltonian of the whole object. It's just like with this radio. A radio produces a unique frequency. So even if you have objects somewhere there, they don't listen to it because they are not tuned to this frequency. And you're right, it's very hard to isolate these two level states. It's because the state can in fact, interact with other states. For example, if you have a trapped ion, it has also other states. These other states are sometimes useful, for example, to measure. Sorry, in this talk, I will not describe the whole advanced technology behind the scenes, because yes, to describe this, all these levels, you need some underlying description which is based on many levels. Yeah? And now the question, the aim of quantum computers is to isolate this basic unit to two levels, and to say that any interaction with other states is washed out. It's removed. One of important point in this picture is adiabatic approximations. If you have, for example, the strike frequency, say 5 gigahertz, then you try to manipulate this qubit with a pulse, which is of this frequency, yes, 5 gigahertz, but the pulse is very low. So the envelope is a kind of low frequency. And then you can use a adiabatic approximation, which says, okay, only objects that have this particular frequency are sensitive to this qubit. I think it's just like if you have, I don't know, a remote drone or a radio also, which just works with a given frequency. And the same idea is with qubit. This qubit is an isolated unit of a certain frequency.
Sorry.
Yes.
Just to be sure, because frequency is in principle continuous number, like so you can describe
Yes.
number.
Yes. Right.
But here you probably mean like it's quantized. So
Yes.
In a sense, so it's not like radio example is giving a good physical intuition, because radio has also band of the frequency, right? Which is
Also, arbitrary parameter difference in the average difference between the two levels. Also, if you restrict to dimensional space, there is no other Hamiltonian. This is the only one you can write. Yes, but I suggest we continue because
I'm very happy for this discussion already, so because later it will be even hard. Okay, so let's assume for a moment that that's the whole story of a cube. Okay, so now there are at least 3 providers. There are more, I think, now that give you access to quantum computers. At least these 3 I have used. So the first one is IBM Quantum. I don't know why they always do religion. In God we trust. I don't know. Hey, for me no problem.
but maybe this is the gap for them.
Okay. This is IQM. No, this is from Finland, so it's not here. Okay, and the last one is IonQ. They are mysterious because now they are offline. So to tell you the secret, which is not a secret, but they are on. It's a long, because the trap for ion is something like is elongated, so it's not a square or a rectangle here. So ions are somewhere here. I don't know. From where they are. Furthermore, there is maybe because you also may know D-Wave. D-Wave is also another computer, but D-Wave has a different role because D-Wave is more about quantum annealing. When you want to find a ground state, it also has access, but I didn't try with qubits. Okay, everything has to be cooled down to microkelvins. You have a different number of qubits, so it's very small, as you see this coin. It's very small, but there are some qubits, maybe not so many as in a real computer, but still about 100. There is a new technology, Huron, which is a similar number of qubits, but less smaller device. I remember that Jakub project also here about IQM. So I think we are as good as IBM, maybe even better. Okay, and Ion has 25 qubits. Now it's open. Well, this is now a topology of example here, IBM Eagle. It's in reality, it looks like a honeycomb lattice. It's just modified to have all these qubits in a line. These colors are representing some errors, but the main thing is that all these qubits have different drive frequencies. That's what's important. There are connections because you want to make two qubit operations and quantum computers and so on. So there is some connections. It's not all-to-all connections like for ions, but still you can move away, maybe not very far, because whenever you move information from qubit to qubit, you lose some. So it's not good to I remember when I started with this Eagle, I wanted to entangle qubit 0 with qubit 126. It doesn't work. It doesn't work. So the slide is so long that there's no entanglement at all. They have different frequencies. Okay, now what are the operations for qubits? There are three types of operations. One is single qubit operations. You have a kind of block rotations. I will maybe skip lecture on block sphere, but it means that you can maybe just go back to this, that you make some linear operation on this vector alpha theta. And in the language of block sphere, you make either a rotation pi half or pi, or even now you can even make an arbitrary rotation. You need a pulse which corresponds to this drive frequency. It is envelope. So for instance, if you have this 5 gigahertz, then it corresponds to time below 1 nanosecond. So this pulse is about 50 nanoseconds. And you can make some phase shift because it's a complex number, so you can make some shift between cosine and sine component. For ions, it's a bit mysterious because IonQ, for example, does not open, it does not show its technology, but in some papers they say about stimulated random transition, so 2 lasers of different frequencies. 2 qubit, there is a connection, and it's like maybe I'll come back to this radio language. 2 qubit operations, it looks like you have 2 radio set from radio RMF, so and there is some cross interaction. Okay. There are 3 types of operations. It depends on some errors and trials. C0, which is controlled node, CZ, so controlled phase flip of 1 qubit. And IBM now uses so-called ECR, echoed cross resonance. They say that it's more efficient. And the longest operation is measurement. Measurement is a bit different because now we are going back to this 2-level structure. To measure qubit, you have to map it to something else. So you need to meet a different frequency. It's not a tri frequency. Something which responds, has a response to the state of the qubit. So it can detect whether the qubit in a state 0 or 1. It is also very some mysterious IQ kernel. So the measurement is not 0 or 1, but it's a complex number, and you just distinguish whether it's on the left or the right, something like this. But usually IBM and our computers simply map it to 0 and 1. Again, there is this adiabatic approximation. So the pulses need to be small enough to not to prevent transitions to other states, which means some kind of leakage to say other qubits or different states of the same at the same position. Okay, like Hamlet said, is qubit a qubit? How can we verify if we have a qubit? So like with this apple, is a good apple or not? Is a good qubit or not? So let's check it. To check a qubit, you have to make a kind of probe. The first idea is that you prepare a qubit in some state and then measure it in a different state. So you have an initial state and final state, and what you measure is, as always in quantum mechanics, kind of probability. The formula for this probability is very short. It's trace of product of two matrices. You can make it a bit more complicated. Instead of prepare and measure, you can make a measure and measure protocol when you initialize a two qubit states, which is an integral state, and then send one party to the left, another party to the right. And again, you can probe whether each party is a qubit. Is it a two-level state? How to check it? The idea is very simple. First-year studies. Qubit. This is a matrix, density matrix of a qubit or an observable. It's a complex matrix, 2 by 2, and it has 4 parameters: A, B, C, D, Z, like for matrices. So if you have this probability, which is a linear function of two matrices, then the determinant, if you take 5 of them, so one more, must be equal to 0, because there must be some linear dependence. You have only 4 dimensions, so any determinant, any matrix which is 5 by 5 will have to have some column or row which depends linearly on other columns or rows. So this determinant must be equal to 0, which is very useful because it's not like Bell inequality when you have to be above some bar. You just have to be exactly at 0. Of course, it's not that you have strictly 0 because there is some statistical error. The statistical error, if you calculate, is based on the adjugate of this matrix. So you, like Laplace decomposition, you take a matrix of minors. Remember that if the determinant is 0, you don't have the inverse matrix, but you still have the adjugate matrix. And this adjugate matrix is responsible for this statistical error. We put this probability, and now let's check. Okay, and this is the first check last year from IBM. It's also from Nairobi. Nairobi is now discontinued. It's in old technology from IBM research program Access, when we used my team was the most using team of we used most of IBM resources. They asked, what we do? This is what we do. We checked if there are qubits or qubits. So you easily see that this witness, this determinant, is more than 10 standard deviations. Look that there are 2 different ways with I and why there are two different kinds of measurement with witness. Let me go back to this determinant. If you remember Bell inequalities are linear, so they probability always enters linearly into Bell inequality. Here, determinant is a nonlinear function. Why it's important? Because you can easily cheat this picture if you suddenly change this probability. So if there is some change of calibration, then it may change this probability, and from two different experiments, you cannot tell the correct probability. To prevent this effect, we made two different ways of calculating of this witness. The first one is take all jobs. Maybe to tell you a bit about how we make this experiment. There is a basic computation unit in IBM, but also in other quantum computers. It's a job. In each job, you send them a number of circuits, so a number of experiments, and a number of shots. So each experiment is repeated for a certain number of times. Here it's 10,000. In Nairobi, it was even 100,000. But this because you have some limit on circuits, and you can take more. So the first one is take all jobs, so all these basic units, then probability, and then calculate the width. The other way of calculating, which here gives exactly the same results, but maybe here it's a bit different, is firstly calculated for each job, because we can assume, I hope, that a job has a single calibration. There are some calibration differences between different jobs, because IBM, I think two times a day it makes a break for calibration. A calibration does not mean that a qubit becomes something completely different. It just calibrates pulses to tune to frequency, because there are some and whatever way you use to calculate this witness, the result is the same, which also shows that it works, but it's not just because of calibration. Okay, that's one example. When we wanted to push harder this test and simplify it. The simplification is protocol is like here. It also shows how it is done in practice. You start from state 0, which is always in quantum computers. You first make a pi-half rotation on this block sphere, and then make another rotation, which is now parametrized, which is also pi-half rotation, but around the axis, which is turned by the angle beta. If you remember some mathematics studies, you can easily find out that on block sphere, what you get by these two operations is Fizyki curve. Fizyki curve, if you remember, is you take a ball and take a cylinder, and do not push this cylinder to the center of this ball, but shift it in such a way that its radius is half the radius of the sphere, and it is tangent to the sphere at the surface, like here. And this is the Fizyki curve, and by these two operations, you can send, you can prepare the state which is on the Fizyki curve, and also the measurement state is also on this Fizyki curve. This is the parametric equation for the Fizyki curve. Why it is important? Because now you have only two independent parameters in this test. One is the angle of the prepared state, and the other is the angle of the measurement state. So this beta and phi work as this index from 1 to 5. Okay, results. These are, I'm cheating a bit, because I'm showing you the most faulty qubits. It's not that all of them are faulty, because if you, let's come back to this grid. If you have 127 7 qubits, it's not very efficient to take to measure a single qubit at one time. What is efficient is take say qubit 0, take qubit say 15, take qubit here, whatever, just with some distance between them, and then in a single experiment you can test many qubits at the same time. And here the results are just from the two most faulty qubits in two different tests. And you can see that it's not always that you have that this weakness is very large. Sometimes it is about 500 standard deviation, but not on here. It's on the level of 5, but it depends. Okay, it also depends on the month. So from time to time, one qubit is better than the other. But what you can see that indeed this test can tell you that some qubits are faulty. They don't pass this test. So let's come to this test. So if they don't pass this test, something is wrong. Now, what can be wrong? Assumptions, so that we have a two-level space, or independence, because in each of these tests we need some independence between, say two states or preparation and measurements. Okay, but not only IBM, we also IQM has given us 1 hour free, so we used it to make this test. You can see on this map that some qubits were okay, those green ones, 20 qubits, but all the red ones are again faulty. So it's very large violation. You can see far here it's 20 standard deviation. So again, for you see that I haven't used these blue ones to keep some different distance between one qubit and the other. But it is not very important because they are independent, so should not change. The final test, and it was quite hard to run it, is on IonQ. With IonQ, there is a problem because IonQ is very expensive. It makes you pay for each gate, so it doesn't work to test all qubits at once. So we took just one qubit. Okay, and we have sent 20 jobs. Probably we made some mistake in sending them because IonQ told us that all this experiment cost about $200,000. I didn't pay it. Why? Because I had a Google Cloud account, which has a limit. It gives you a free $300. Okay, free, completely free. Okay, this is what some Hungarian guy told me was kind of how to cheat them. But now IonQ is offline, so we cannot repeat this experiment. And now you see that it's a bit better because sometimes with a single qubit is good, but for some jobs I gained some strange effects. Unfortunately, we cannot repeat this because, as I said, it's now offline. We can try probably another ion is penalty. If I remember, we are talking to people who can repeat this experiment because we would be very happy to check is it correct or is it some our mistake. Also because IonQ runs jobs in a different way. So if you have jobs in IBM, each you have different circuits. So you have circuit 1, circuit 2, circuit 100, and now the next shot, so circuit 1, circuit 2, circuit 3, and so on. So, and now in IBM, you can be clever and shuffle the circuit to avoid the memory effect. In IonQ, we cannot do it because it runs like this. You have experiment 1 and test it for 1,000 times. So it's evidently there could be some memory effect. We don't know it. We have to check it, or we should change the way of making it. But at least from this test, there is something wrong. Again, okay. Can you go to a different way? This measure and measure. It's more complicated. You need quite different setup. So you need 7 qubits. One which entangles party A and B, and then you need 3 measuring qubits. Why 3? Because you need 5 outcomes. From a single qubit, you have only 2 outcomes. You need 5 outcomes, so even 2 qubits are not enough. You need 3 to have 8 outcomes. You can combine 4 of them into 1 outcome. When you take the other 2, and from this complicated, this is this gate Q. Then you again get from there are at least 4 different ways to find this witness, and again it's at least about 5 standard deviations. Okay, here it's even close to 10, and again shots in Nairobi it was 100,000. For Brisbane, Nairobi, it's now limited to 20,000. Okay, now the most recent one is to reverse this idea of measure and measure. So we call it prepare and prepare. You prepare 2 independent qubits, and each one sends its qubit to a referee, which is M in the middle. And again, depending on these preparations, the referee does not make any choice, it just measures. But again, you can get this 5x5 matrix. And here are 2 examples of Brisbane and Sherbrooke. Again, violation is again above 10 standard deviations. This L and S. The difference is if you make experiments on IBM, it gives you 2 options. One is as soon as possible, and one is as late as possible. The default is as late as possible. Why? Because you want the qubits to stay coherent. So the later, the better. But as you see, in both cases there is violation, but in as soon as possible it's smaller. Okay, so it's smaller. So there is some difference. Okay, and the last thing, not only the null tests are not only testing the space of qubits. This one is a very old null test. It's no signal. If you know Bell test, in Bell test, it's very important that 2 parties do not communicate. It is an assumption of Bell test, and you can verify. Of course, IBM is small as this coin, so it's not relativistic distance, but still, the fact that if you, I will show it here. If you, where is this qubit? 49 and 66. Okay, just look. The distance is 1, 2, 3, 4. Okay, these 2. And if you take these 2 qubits, and and you make a very, very long experiment. the 120 millions of trials per setting. So you need a different setting. We didn't make any penalties. We simply measured A and B. And you can find this violation that it's maybe not 10 standard deviation, but it's definitely above 5. Here is the error. So again, there is some problem. And now to summarize. So now the question is, so what could be the reason why all these tests somehow failed? The first one is when I talk to people, when they say, okay, but there is a leakage. Leakage. What does it mean, leakage? If you have states 0 and 1, you probably have states 2, 3, and so on. Also, if you have one qubit, it's probably another qubit nearby. It can also take some information. But there is a problem that this leakage, if you calculate it from, say, adiabatic approximation, is so small that these values, I don't know if you notice the order of this violation. This order of violation is 10 to minus 4. So it's so the leakage is smaller than this violation. And if you really want to check how this leakage affects this weakness, you need a square of it, which is 10 to 12. So I don't think that it's likely. Crosstalk. Yes, crosstalk could be important, but only if you take into account 2 qubit gates. And again, this error is maybe larger than leakage, okay? But this error mainly contains the space, the two-level space. So again, the question is, okay, so where does it escape? And the final argument is, maybe let me go back to this Vivian. But the only difference between these states is hidden in the phase shift. And if it's only the phase shift, then leakage would need to be coherent, which is not what we expect. So memory, we try to shuffle angles, except as I said, IonQ. Here we couldn't shuffle, but we cannot repeat it. So here is a big question. Okay. Maybe there is some fundamental origin. I will not expand this section because I think the first question is to repeat this experiment and answer if it can be really an effect of leakage, crosstalk, or maybe some memory. Okay, that's almost all. I just want to say that I'm not alone in my team. We have Jakub from also university, Tomek, who also worked with you, I think. Another Tomek and Spanish guy also. And you can read it somewhere. Thank you.
Thank you very much, Anna, for the talk. Now let's start the questions. Okay, then I start. So you showed us the worst qubits. Let's say on the IBM. How do the average, so to say, perform, like average performers?
So it depends on which test do you do. So if on IBM, it's usually that say about 1/3 of qubits, if you take them at random, work back. So the good
before you continue, what is bad for you?
That is
5 deviations.
5 deviations. Say 5 deviations. Okay, so 5. So this limit 5 deviations is bad. So about 1/4 is bad. If you take this last one, maybe this one, prepare and prepare. Here it was very hard to find a bad qubit, so almost all passed them. So we took, if I remember, 12 qubits and from each device. So only one of 12 was wrong, was bad. Okay? So here it's not bad. I don't know how about this new technology, Heron, which is not yet publicly, maybe you have access to it. We'll talk later. Because maybe this new one is better. This is what I would be happy to check. So for now, it's like, it's kind of 50-50, I would say.
I think Wojtek was first.
Thank you very much for the talk. Actually, I have a non-physical question, but I guess it's related because physics is still there. So do you see any potential for commercialization of this approach? In a sense, you know, whenever you buy anything on the market like non-quantum computing, there are established practices for customers. There's some benchmarks, some external certificate agencies, and actually you as a consumer can have some.
Yes.
And of course, now quantum has been very big buzzword, although if you trust NVIDIA chairman, that he said 2 days ago that he doesn't see any application in 20 years, even though, let's say, you think, and the stock market of the of the Nasdaq went down. But anyway, I think, you know, this goes direction that you can envisage that I can in the future come to you and say, look, here's some money, test this service and tell me how much quantum there is, how many qubits.
Yes, I would say this is exactly what I would be happy to sell it as a kind of certificate. So the problem is that I can tell you I have met Jay Gambetta, which is the chief of IBM Quantum, and talked to him. And he said, okay, just send it to my collaborators, and it was somewhere deep below his desk, I think. But yes, I believe that this kind of testing should be popular and should be commercialized just to test. For example, if you want to buy access to quantum computer, Poznań or whatever, now you can tell them, wait, give me a free hour and I will test if your qubits are good, okay? And then I only buy your qubit. I guess so in this way it should be practical.
Oliver?
Yeah, thank you for an interesting talk. So there are quite a lot of different ways to benchmark and test quantum computers, right? People have cooked up.
Yes, there are different ways.
So let's say I take your method and I take, I don't know, something that people have been doing this for a long time, randomized benchmarking or fidelity, whatever you like. Do you find the same qubits about using your method as theirs, or are you measuring like different types of bands? Do you agree?
Well, I agreed that there are various ways to test, to make this benchmarking test on qubits. There are this randomized benchmarking. I know that there is this Google big paper on crossing some threshold of benchmarking. I think all those benchmarking tests are good because you test different sides of these quantum computers. In this way, you focus on the space, whether it's two-level or not, because you don't make any other assumption. This is all the assumptions that you make. If in other tests of benchmarking, you make simply different assumptions. You also test different assumptions, whether you have some limit on errors or whatever. So I would say it's not that our test is better than others, it's just complementary. So you can test here whether you have really two-level space, and probably the more benchmarking tests, the better.
Okay. But you haven't like directly compared them to see if you like.
We haven't seen. I would say it's very hard to compare exactly the same qubits, for instance. I once checked a German paper. They also have found a kind of leakage and crosstalk, but on a different device, which is no longer now operating. It would be good to say have a contact. Maybe one thing that I prepared. in this last no signaling test, when we have put it on archive, then Simon Stotz, who is from Waldorf group from Zurich, told us that they want to beat us. So they want here it's 120 millions, and they will do an experiment with $500 million, so a bit more. So and I think there will be some comparison, but I don't have I will try. So my promise is what I will try to follow your idea to check exactly those qubits which other groups find, for example, faulty.
I had two questions. The first one was very close to the question of Oliver. So the second is that there's recently quite popular network atoms, and there's this companion looking with different technologies. So what's your opinion actually? Is it indeed that this quantum computers based on network atoms would be better or not?
I don't know. I also heard that they have very good quantum computers. What I can say, it would be good if what I like in this whole idea is when it's commercialized, because then everybody can test and answer this question: are those qubits good or not? So at the moment, I would not say that one technology is better than the other, but every day I'm reading and checking whether there are some news that this one is better. So in short, I don't know. If it's better, I will definitely check them too.
Okay, more questions? Maybe from the online audience? No? Then Oliver, please.
Sorry, yes, I'm kind of not listening, but let's see if we have Schwanietz, who is an expert in detecting errors in quantum measurements, right?
Yes.
So essentially my question is, does your approach, is your approach sensitive to errors in measurements? Or like, will it confuse an error in measurements to an error in the qubits?
They are more sensitive to measurements in qubits, because all we assume is the space of qubits.
Well, you assume the measurement works as well, right?
But okay, but where it may be important, if, for example, if you take this kind of measure, if, for instance, the measuring device of one party is somehow correlated with the measurement in the party of the other party, it may affect this experiment. So some cables which go out of these computers, if they are close to each other and there is some short circuit or whatever, it may affect, it may have some effect. About cables, I also remember this neutrino story with some cable. So cables may be faulty also here. I don't know, but I'm not the guy that put these cables.
I can then comment on that, since we were last year visiting IQM in Finland, and a big part of the talk was about cables. Was really about cables, and the limiting factor that is usually quoted about 1,000 qubits in a transport device. And I understood from talking to IQM people is because of the cables. Because there are special cables that have to go all the way from room temperature to 10 millikelvin cryostat that carry all the driving signals and the readout signals. IQM people told us there is only one company in Japan that makes those cables, because basically you don't want to create a thermal breach. And one cable is, I think, $1,000. So if you have to implement 500 cables, that's already quite a cost. So yes, cables are important in quantum computing.
Maybe one comment to this is that from my perspective, I have to trust the providers. I cannot go to America to check on the are you okay. So I'm like you are at the market. Somebody is telling me, and I can only tell is it good or not. I cannot go to say the apple farm when they grow all those apples. I just buy the apples, and here is the same. I don't have the access to all these cables. I just have to trust them and can tell, okay, are they as you promised or not?
Okay, more questions maybe? Then I have the last one. Let me be a bit of devil's advocate. So, okay, you detect that qubit is not really a qubit. And somehow connected to other questions, like to other benchmarking, but how important is that for actual tasks?
Okay, yeah, very good questions. The problem of this leakage to external states is that it makes problems with error correction, because usually error correction protocols assume that qubits are qubits, so they have only two-level space, and you can make some correction, but you know that the error is only within this two-level space. But maybe if we could identify that there is simply just a state 0, 1, so the state 2, and include it in error correction, then it may still work. But this is what would come out of this research. But you have to add other states to error correction.
Okay, so let me ask one more time. James, no. Then let's thank Adam again.